this problem from sequence of function and its uniform convergence. And here given a sequence of function like this fnx, this is given by in the three different interval. Okay, but here the total interval is 0, 1, and this interval split into three portions from 0 to 1 by n to 2 by n, and 2 by n to 1. Okay, and in the first problem it is so that, or it is given that we have to find the function f which converges fn. That is, we have to find the limit function of fn, limit function. Okay, because we know that limit n tends to infinity fnx, if we get fx, then fx is said to be limit function of this sequence of function. Now to find the limit function, we get any c belongs to open interval 0, 1. Okay, otherwise c, we take c is 0, and in another case we take c, this is equal to 1. In three different cases we have to find the limit of the sequence of function. And if we take c belongs to 0, 1, then we know that there exists natural number p greater or equal to 2, because here n greater or equal to 2 is given. So we get natural number p greater or equal to 2 such that 0 less equal to 2 by p less than c. Also here it is given that c is lies between 0 and 1. So always c less than 1. So we write less than 1 here. Okay. Now if we take n, this is greater than p or greater or equal to p, then we can write 0 less equal to 2 by n less equal to 2 by p less than c less than 1. Okay. That is, for all c belongs 0 and 1, we get there exists n greater or equal to 2, because p greater or equal to 2, so n greater or equal to 2 also, such that 2 by n less equal to c less than 1 or less equal to 1. Okay, less than 1 we write here first. That is, this c we take here in between 0 and 1. This c lies between in this interval 2 by n less equal to x less equal to 1 or less than 1. So in this case, limit n tends to infinity fn x, this is equal to 0 for all x belongs to 0 and 1. Okay. Now here we put c equal to 0. Then we go to this interval, because here x equal to 0, and clearly if we put x equal to 0 here, then we get fn 0, this is equal to 0. So we get fn 0, this is equal to 0. Similarly, if we put x equal to 1, that is c equal to 1, then we get x equal to 1, that is it is also 0. So fn 0, this is equal to 0. So we can write this relation as limit n tends to infinity fn x, this is equal to 0 for all x belongs to closed interval 0, 1, because we add here 0 and 1 in both sides of this interval. So we get this. That is, we say that here the function fx, this is the limit function, this is equal to 0. So we first find the limit function fx, this is equal to 0 for all x belongs to 0, 1, and this is the first answer, or this is the answer of the first problem, right? And for the second problem, show that the convergence of the sequence is not uniformly by establishing that limit n tends to infinity integration 0 to 1 fn not equal to integration 0 to 1 f. Okay, here we use the theorem of uniform convergence that if f and x is R integrable, then if fn is uniformly convergent sequence of function, if fn is uniformly convergent sequence of function, then fx must be R integrable there. Overall, we also get a relation in this theorem as limit n tends to infinity integration a to b fn x dx. This is equal to integration a to b fx dx, or we can write this relation as this is limit n tends to infinity fn x dx. Okay, and here a and b in this problem is 0 and 1, 0 and 1. Okay, here also 0 and 1. Now we have to find two integration. We first find the integration 0 to 1 fn x dx. Here integration 0 to 1 fn x dx. We split this integration into three intervals. The first interval is integration 0 to 1 by n, and the value of this fn x is n square x dx, and the second interval is 1 by n to 2 by n, and the value is minus n square x plus 2n dx, and the last interval is 2 by n to 1, 2 by n to 1, and this is 0 dx. So the value of the integration is, this is n square into x square by 2, range is 0 to 1 by n, and this integration is minus n square x square by 2 plus 2nx, range is 1 by n to 2 by n, and this is 0 because the integrand is 0. So by putting the range we get, this is n to the power 2 into 1 by 2 n square, because the upper range of x is 1 by n, plus this is, we put 2 by n and lower range is 1 by n, so we get minus n square by 2 into 2 by n square minus 1 by n square plus 2n into 2 by n minus 1 by n, and the final result of this integration is half. This is minus half into 1, because this is 1 by n square, and this is also plus 2 into 1. Okay, so we get, this is half cancel out, so this is 2, right? Now if we take the limit of both sides, then we get the left hand side of this relation, and limit n tends to infinity fn x dx, here integration 0 to 1, this is also 2, because 2 is a constant independent of the limit n tends to infinity. Now we go to this side integration, and the integration of right side is integration 0 to 1, this is fx dx, because limit n tends to infinity fn x, this is the limit function, this is fx, and we get here fx is 0, fx is 0 for all x belongs to 0 1, so we get the limit is also 0. So we can write this integration equal to 2, but this integration is 0, that is not equal. So left hand side, this is not equal to right hand side. Okay, and since this left hand side not equal to right hand side, so we say that this sequence of function must not uniformly convergent. Okay, and we say that since this is proof we already have, then we say that fnx is not uniformly convergent. Okay, this is the proof of this problem.